Oh, good morning, everybody, and thank you for attending this morning's masterclass. I'm David Reid. I am one of the mechanical and electrical design engineers here at Mesh Energy. And this morning we're going to be talking a little bit about battery storage. So we're going to go through some of the basics, how it integrates with PV, and a few other bits and bobs. So without further ado, let's get started. So just to run through what we'll talk about today, we'll start off with a brief introduction, firstly to Mesh Energy. I'm sure an awful lot of you will be familiar with what we do and who we are. Then we're going to look at a little bit of the energy hierarchy. So that's sort of the basic principles of construction that we like to try and sort of push at all times. So I'm sure most of you will have heard us droning on about this time and time again. So I won't spend too long on it, but it is quite important that we sort of put this in context. Then some of the basics about battery storage, what it is, how it works, some definitions and terminology. There's a few sort of electrical bits in here that might be new to a few people, and then a little bit about why you might want to use battery storage. Then we'll go a little bit more into the technology, some of the system components, and then talk about integration with solar PV. And we're going to look at two specific systems, which are AC coupled and DC coupled systems. That's the sort of two overarching sort of sides. Then a little bit about charging batteries from the mains, why that might be a good idea in some cases, and also why it might not be. Then we're going to look at island mode, and then also backup capability, and how a sort of typical home battery storage system differs from an uninterruptible power supply UPS system. Then a little bit about the controls that a user might see, before we dive into some of the sort of regulation and what I've called the red tape part. So around DNO permissions, so that's the distribution network operator permissions. A little bit about the case for investment, and also about time of use electricity tariffs. And then finally, we'll finish off with a little bit about sort of the key takeaways, and a little bit about how MESHWORK and how we could sort of help you with one of these projects, and then a little time for questions at the end. So what I'm hoping is that the presentation will take about 45 minutes-ish. That'll leave us about 15 minutes of questions, and we should be done by around 11 o'clock. So let's get started. So most of you will have probably seen these slides before. They're pretty much the same in every presentation. I won't dwell on them too long. But who are Mesh Energy? We are an independent energy consultancy, and we look to sort of clarify the renewable energy landscape for our customers. And we do our very best to sort of give impartial, practical advice to our customers, whether that's architects or end users. So the most important thing is we try and look at the whole development in a holistic way. So rather than trying to specify a particular technology or push a particular technology, what we try and do is look at what the best sort of set of technologies for your particular installation is. So let's talk a little bit about the energy hierarchy. So moving from left to right on this slide, we start with the most important things, and the things that are fundamental to the building, and things that you really can't design your way out of. So can we put the building in the optimum position on the site? Well, yeah, I mean, if you're building a new build, you might have that option. If you're retrofitting, probably not going to have the option of changing the orientation of the building or moving it around the site, but it's always worth having a think about. Then we're trying to reduce the amount of energy the building will use from first principles. So that's increasing the amount of use of daylight, natural daylight, increasing the use of natural ventilation rather than mechanical ventilation, increasing insulation, using thermal mass to its best advantage, and preventing overheating through clever design of solar control. Then we're looking to introduce a reduction in internal loads. So that could be reducing the amount of artificial lighting, and so on and so on and so on, all the way through. But you'll see the renewables part here, which is right over towards the right hand end, which is where we're sitting, is really quite far down the food chain. So really, we should have considered quite a lot of things before we get to renewables. So it's just worth bearing this in mind. This shouldn't be your sort of first stop. This should be quite a sort of a long way down the line. You should have thought about lots of other ways of reducing energy or making a building more energy efficient before we get to this sort of stage. And sort of the takeaway from this is that always adding low carbon technology, is not a substitute for getting the building fabric as good as possible from the outset. Okay, so let's have a little look at the basics of battery storage. Now I've sort of told you the bad news about why you should be looking at it quite far down the road. Let's look at some of the basics of the actual technology we're here to talk about. So what is battery storage? Well, battery storage is effectively a chemical means of storing electrical energy. Now, most of you will know that that electricity is generated and must be used in a conventional system at the same time. So you can't, using most conventional means, you can't store electrical energy. So the national grid produces electricity at exactly the same rate that is used by consumers, and you'll see that that demand going up and down throughout the day and the night. And if you start looking at time of use tariffs, which we will a bit later on in this, you'll see that actually the cost of electricity varies throughout the day and night, as one method that the grids use to try and get particularly commercial users to use electricity at the point where it's actually produced. Effectively, what the battery does then is it adds a reservoir into the system. So if you imagine I always find it quite useful to think of electricity as analogous to water. So if you had a spring that was coming out of the ground, producing lovely, fresh, clean water, and then it just went straight into a pipe and then to a tap, you effectively have the choice of, you either use that water or you have to leave the tap on and it runs down the plug hole and away. If you put a reservoir in there, you can be topping the reservoir up and then using it as and when you need to. And that's basically what a battery does. So here's a few of the sort of basic definitions, a few of the basic terms that we're going to use throughout this presentation. So energy. So energy is the capacity to do work. It's measured in joules or kilojoules, where 1,000 joules is 1 kilojoule. This is sort of basic GCSE science, hopefully, so this shouldn't come as any sort of surprise. Power is the rate at which work is being done. So it's how fast we're using energy. So if you imagine that you had a steak and you fed your steak to a domestic cat, that steak contains a certain amount of energy. The domestic cat is going to eat that steak a lot more slowly than a lion will. A lion will probably eat it in one gulp, and a domestic cat will eat it, over a few minutes. So that's a similar sort of thing to power. If you think of the steak as being the energy and the power as being the rate at which it's consumed. Battery capacity, and this is where people quite often get confused, and the main reason why I put this into the presentation is measured in terms of both power and time. Now, power is already a time dependent thing. So if you take power, which is joules per second, which already has time on the bottom of the equation, and then you times it by time, then actually what you find is the times then cancel out, and you end up back with a unit of energy, but it's expressed in terms of this thing called kilowatt hours, which basically is if you had a 1 kilowatt load and you ran it for 1 hour, how much energy would it use? And the answer is 3.6 million joules. So obviously, working with such large numbers is quite inconvenient. So hence, that's why kilowatt hours came up. And a typical battery that you might put on a sort of typical house might be in the range of between maybe 5 kilowatt hours and sort of 15, 20 kilowatt hours. So they're not, so you're talking about relatively sort of sensible numbers. It's quite easy to work with. The next thing we're going to look at is something called depth of discharge. So depth of discharge, or DOD, is how much of the battery you've actually used. So it's a measure of fullness of the battery, so how much of that reservoir is left, and it's expressed as a percentage. So 0% DOD would mean that you've used none of the battery. The battery is full, so it's 100% full. And 100% DOD would mean that the battery is completely empty. And again, it's a slightly sort of odd way round of thinking of things. But the reason it's important is that if you persistently run the batteries to very high depths of discharge, then it can actually affect the life of the battery. And because of that, most battery controllers won't actually allow you to run the battery right down. And different battery chemistries will also affect that. So if you have a battery for a sort of normal car battery, a normal car battery uses very thin plates of lead, lead acid battery, and if you run it to a high depth of discharge, the electrodes will actually start breaking down. Other types of battery, so the lithium-ion batteries that are more common now, can cope with higher depths of discharge and work more happily. So again, it's matching the type of battery that's chosen to the way that the way you're going to use it is quite important. And because of this, many batteries will have an actual capacity, which is effectively what the entire 100% depth of discharge capacity is, and then a usable capacity. And quite often the usable capacity will nearly always be a bit lower than the actual capacity of the battery. And typically you'll get about 90%-ish out of the battery, something like that. So the next thing we're going to look at is just the difference between AC and DC currents. Again, hopefully this is really, teaching granny to suck eggs, but AC electricity is what we get out of the mains. It stands for alternating currents. So the current goes positive and then negative with respect to a reference voltage. And this is what we get from the grid. This is what's generated by power stations. This is what works transformers, for example. So all the high voltage lines you'll see across the country, this is all AC electricity. This is what comes out of the plug. When you plug an appliance in, they are getting AC electricity. And a lot of appliances now operate off DC and have a little transformer to change it from DC to AC, a little inverter in there to change it. But it's not what we're going to be using with batteries. Batteries rely on DC, so we've got to convert anything that's AC into DC to put into a battery. And equally, when we're looking at the battery and from PV panels, they produce DC. So if we want to use mains appliances with them, we've got to convert that into AC. So there is a sort of small penalty to pay for doing that. Obviously, like any machine, an inverter isn't 100% efficient. So we get a little bit of a loss when we're doing that. And later on in the presentation, we'll look at a couple of different these AC and DC coupled systems and some of the advantages and disadvantages of them. Okay. And then the last bit I'm going to touch on in this section is the importance of time of use. As we know, electricity doesn't cost the same at different times of day in wholesale values. So although you might pay a flat rate for your electricity at home of maybe typically 15 pence per kilowatt hour, the actual wholesale cost of that electricity varies throughout the day from a few pence at the really off-peak times, up to significantly more than 15 pence at the very, very highest peak times. So thinking about when we use our electricity is quite important when specifying a battery. It's also worth thinking about the fact that exported energy is worth less than imported energy. The same as with any market. If you sell something, you would expect to receive less money for it than if you buy it. Because there's obviously a sort of markup in there. As sort of talks about, the wholesale cost of electricity varies every 30 minutes, so you'd expect, and typically the cheapest rates are in the middle of the night. Particularly in the UK now, we've got a lot of offshore wind generation, and it's not very turn off and onable. So you can't. So the cost can actually go negative in the middle of the night when the wind farms are producing loads of energy, and there's nobody really trying to use it. So the grid, the price drops and drops and drops, and eventually can go negative. Generation from solar PV obviously varies with time as well, depending on where the sun is in the sky, where what the intensity of it is, how cloudy it is, all those kind of things. But you can average that out quite well over a day. But what you will see is that for most households, generation pattern won't match the consumption pattern, and that's particularly true in houses where people are at work for most of the day. If you're out at work, obviously you're probably not going to have that many appliances on, that many lights on, all those kind of things. So matching the consumption, or getting a good idea of the consumption pattern, is quite important, because what you're wanting to do is you're wanting to ensure that you're using as much electricity that you're generating on site as possible, or putting it into a battery, rather than exporting energy for periods of the day at low cost, and then importing that electricity back at high cost at other times of the day. So that's really what a battery can do for you. So why use battery storage? Well, I've kind of covered it already. Maximize self-consumption from solar PV. Allows you to buy electricity at off-peak times and use it at peak times. So that's charging from the grid. There are some grid-connected services that allow you to earn a bit of money. And then the sort of final one, let me just go back one, is that it can give you a little bit of backup in the case of a power cut. Obviously, in the UK, power cuts are relatively rare. They tend to be of relatively short duration. But there are some things that it's really useful to be able to have. And if you live in a rural area, maybe you're supplied by overhead lines, you're probably not going to be the first priority if there's a big storm or something to be reconnected for power. So you might be offline for a few hours, or maybe even a day. It's worth, that can be quite valuable to some people, that ability to have a backup, certainly for a few key services. Okay, so let's get a bit into the tech. We're going to look at some of the major parts. So here's a sort of typical house. We've got our electric vehicle here. It's been charged from a little charger, or charging point. The charger is actually in the car. We've got some solar PV panels on the roof. They're generating electricity. We've got the grid feeding into the system, and then we've got a number of electrical appliances around the house. So we've got maybe a heat pump here. We've got that's probably a fridge freezer. Maybe that's maybe the freezer, maybe the fridge, the washing machine, tumble dryer, TV, internet connections, etc., etc. Got somebody's study bedroom up here, so they're working on their computer. All of these things are using power. So the question is when that car goes out and it's not being charged, when somebody goes out and look, most of these appliances are switched off, what's going to happen to this energy that's being produced by the solar? And the idea is that in most cases at the moment, batteries are paired with solar PV to reduce the amount of export from the system. That doesn't necessarily mean that you must do that, but that tends to be the way they're used. Controls in the battery system, and we'll touch on this more a bit later on, can ensure that they can actually predict the amount of solar that will be produced by the array on a particular day. So based on the date and based on historic data, it will work out, I think I'm going to get about this much energy, and it will ensure that if it is importing to store in the battery at off-peak times, it will leave enough space in the battery for that solar generation to be stored. And you can see that, so it's a sort of whole smart system, really. It's a bit more than it's making sure that the solar panels here work with the battery effectively is quite key. So the actual components of the system. So you've got the battery itself, and the battery itself is basically just a chemical store of electrical energy. It's nothing more than that. There are lots of different cell chemistries around. I did look at whether I should try and cover that in this talk, and I decided that actually it was so in depth and so complicated that and there was no real advantage for most people to understand it, so it didn't seem like a particularly sensible thing to cover. So but what we can generalize is that most batteries operate best at room temperature. So although you can put batteries outside, as we have in this example, we've got a Tesla Powerwall here on the outside of the house. A lot of batteries can go on the outside of the house. You will probably get the absolute best performance from them if they're kept at room temperature. So if they're in a garage or utility room or something, that's probably going to give you the absolute best performance. Costs vary. So the actual cost of the battery and the systems, they vary from around £500 per kilowatt hour up to £1,100 per kilowatt hour. Now, obviously, that's quite a big spread. You're talking about a spread of over double cost of the most expensive to the cheapest. And obviously, that comes with different features and different cell chemistries and all kinds of other things. And different life expectancies, warranties, and all the rest of it. But that gives you a sort of rough idea. And warranties are typically based on the number of charge and discharge cycles. So that could be, and that will be connected to the depth of discharge as well. And also some are just based purely on the time from installation. And they just say, well, we know roughly what the sort of typical number of charge and discharges is, so we'll just do a straight easy time warranty. I think the time for installation warranty is probably a much easier one to work with, simply because most domestic batteries aren't going to go from fully charged to fully empty to fully charged to fully empty. So actually actually defining what a full charge or discharge cycle is can be quite difficult. So at this stage, I'm just going to pause. I've got a couple of comments that have come in already, so let's have a little look. So first one from Charles is, we'll be looking at using the EV car as a source of usable energy for the house. No, we're not going to do that in this one. We've got a question about whether you can record this. There will be a recording of this webinar. It will go up on our YouTube channel, so that will be available, and a copy of a link to that is sent out after to all participants. And the other one from Patrick, does the battery software also link to the internet for weather forecasting and working out what sun power can be achieved that day? At this stage, it's not quite as advanced as that. From what I understand, it's something Tesla are working on, and obviously Tesla are the market leader in home batteries at the moment. I believe it's something that Sonnen may be working on as well, but I don't think it's quite there yet. And then a question from Robert. We would like to use batteries as a power backup for a new house running on 3-phase. Can they cope? Yes, there are some particular things around 3-phase, which I'm not going to touch on in this presentation. But Robert, if you get in touch afterwards, we can talk a little bit about that. There's a few different ways you can do set three-phase up, and we'll touch on them. And also Charles saying, is Tesla the most expensive? No, actually they're not. Actually, Tesla are one of the cheapest, oddly enough. There's a website that I found when I was doing research for this, which is actually only an installer's website, but it's got a particularly sort of awkward name, so maybe a bit careful when you put it into your search engine. But it's called Naked Solar, but they have a table on their thing which shows the different costs, and Tesla actually came out as one of the cheapest cost per kilowatt hour of any of the battery manufacturers, and they certainly seem to be the favorite amongst the installers I've spoken to. Tesla seem to be the most popular in terms of installation. They're easy to install, they're easy to set up, so there's quite a lot of good things in there. There are cheap ones on the market. Give Energy, for example, a little bit cheaper. They're a little bit less proven, maybe, but there's a few on the market. Okay, so back to the presentation. So we're about sort of half an hour in. Hopefully, I haven't lost anybody yet. So we'll crack on. So the other sort of major component of the battery sort of system is the battery controller and inverter. So the inverter is the piece of the puzzle that turns DC electric from the battery into AC that you can use in the house, and vice versa. So if you're charging from the mains, you're getting AC electricity coming in. That AC needs to be converted into DC for the correct voltage, and pushed into the battery. And that part, the controller and the inverter, are quite often in part of the battery sort of unit that you buy. So if you look at a Tesla Powerwall, the sort of bottom 3/4 probably is the actual battery pack, and then the inverter and the battery controller sit at the top. Now this is where there's this sort of disconnect, because inverters work absolutely best in quite cold places. Obviously, we talked about the battery working better at room temperature. So having that integration of the inverter and the controller into the battery pack is a little bit of a compromise. There's, like all these things, there's good reasons for doing it as well, in terms of packaging, ease of installation, etc. So it's just something to be aware of. You can kind of mix and match stuff to a certain extent from different manufacturers and build systems. You have to be careful with voltages and all kinds of other things. So it's obviously an expert job, but the package systems offered by people like Tesla and Sonnen are really, really good. The sort of main thing is that the inverter sets the peak charging and discharging rates, and this is something people sometimes forget, is that you can only push energy into the battery and pull energy out of the battery at a fixed rate, and or a maximum rate. So you can run it at a lower flow, but it's a little bit like your tap. If you turn your tap on absolutely full blast, there's still a fixed amount of water that can come out of that tap. And if you want to get more water than that, you'd have to put a bigger pipe on, bigger tap on, to get more water flowing. And the inverter kind of acts a little bit like that, because you've got a reservoir of electricity in your battery. Doesn't mean that you can get that electricity out at an infinitely fast rate. And different battery controllers and different inverters will have different peak outputs. And also the controller obviously controls when the battery charges and discharges. That's particularly important where you're looking at time of use tariffs, where it might be beneficial to import electricity into the battery from the mains at certain times of day, and might be beneficial to export at other times of day, and also optimizing the use of PV. So that's where the battery controller really comes in, and that's part of the control system. And then finally, there's this bit about AC and DC coupled systems, which is what we cover on the next couple of slides. So the first thing I'll say about this is AC coupled systems are by far the most common that we see. So here we've got our sort of typical AC coupled installation. Up here you can see you've got a solar PV array, you've got the mains on the other side. So electricity can come in through the PV, goes through this PV inverter. So this PV inverter turns the DC current that's generated by the solar panel into AC current that can go into your consumer unit and then off to or fuse board and go off to all your appliances around your house. Your battery sits alongside the consumer unit, so that's taking AC electricity into the battery inverter to charge the battery. So if you want to get electricity from your PV panel into your battery, it has to go out through the distribution board and back out through another inverter and into the battery. And then to get out of the battery, it has to go back out, be converted back into AC, into the consumer units, and then that can obviously go off to the grid, or it can be used by appliances around your house. So this is the most common system, and it's called an AC coupled system. The advantages of it are you definitely want the battery inverter to be as close to the battery as possible, and ideally you'd have the solar PV inverter quite close to the solar panels, and you'd want that in a nice cool location. And you want your panels to be kept nice and cool. You want your battery in a nice warm location. So by separating everything out, you give a bit more resilience to the system. Because say the solar PV inverter goes down, okay, you lose your PV, but your battery still works. If your battery inverter goes down or your battery goes down, then your solar PV still works. So it's kind of giving you a bit more resilience. You can obviously retrofit this to an existing PV system. You can have a large PV system and a relatively small battery and vice versa. You're not having to try and balance the size of inverters and that kind of things. The downside is that it's a little bit more expensive in terms of efficiency because you're converting from DC to AC and then back to DC again. You get about a 1 to 3% efficiency drop. And then you also require 2 inverters, so the cost of installation can be a little bit higher. I'd caveat that with the DC coupled inverters we're about to see tend to be a bit more expensive, so the cost per inverter is a bit higher. So let's have a look at a DC coupled system. So this uses what is called a hybrid inverter. So from here, the DC produced by your solar PV array goes into your hybrid inverter, isn't converted to DC to AC, it just goes straight into the battery. When the battery is producing energy, it goes into the hybrid inverter and then gets turned into AC and goes off to the grid. If the battery is fully charged, then electricity can come straight from the PV into the hybrid inverter, get converted to AC and go to the grid. If the battery is empty and there's no PV and it's cheap rate, electricity can come from the grid through the fuse board into the hybrid inverter, be converted into DC, and then go and be stored in the battery for use at a later date when electricity from the grid is more expensive. So all good. So what are the upsides and downsides? Well, first of all, because the energy that's being produced by the PV isn't being converted to AC and then back to DC to be stored in the battery, it's about 3% more efficient. It can be a little bit cheaper to install than an AC coupled system because you've only got this one inverter, albeit that inverter will probably be more expensive than each of the individual inverters on an AC coupled system. What are the downsides? Well, the main downside is that the power is limited by this single inverter, and that inverter has to be sized to take account of the PV array and the battery. If that inverter ever goes down, then you've obviously got to then try and find an inverter that is compatible with both the battery and the solar PV array. And it might be that spares will be more limited in the future for that type of thing. Typically, inverters have have about half the life of the PV array, so generally, if you're installing a PV array, you allow for replacing the inverter once in the lifetime of the array. And the battery and inverter must be installed in close proximity, which means that this leg here could end up being reasonably long. And you've also got this mismatch in temperature thing that we mentioned before. So, it's not perfect. Both systems have advantages and disadvantages. As I said, the AC coupled system we looked at first is far more common. So mains charging and discharging. Well, why would we want to charge from the mains? Well, let's have a look at the good reasons. Well, mains charging, because the mains electricity price varies during the day, you can basically charge your battery when it's cheap to charge to use electricity, and then when it's cheaper to use electricity, when electricity is more expensive, you can either push it back out into the mains or just use the electricity from the battery. You can also, with some schemes, get really good electricity rates by handing control of your battery to the electricity provider, and that allows the electricity provider to effectively use your private reservoir as part of the network, and that allows them to generate some more cash themselves, but they pass a proportion of that onto you, so it can give you a really good return on investment from that point of view. And the third thing is that backup power levels can be managed, so that if for example, there's going to be a power cut, you could use the mains to, the DNO contact you and say, we're doing work in your area. You could actually set the backup power level on your battery to being a very high rate, a very high level, so that your battery's going to be absolutely fully charged when the electricity is cut off. So those are the sort of main reasons why you might want to use mains charging. So what are the options for mains charging? Well, there's three main options, and the first of those is that you can effectively say, right, I'm not going to ever charge my battery from the grid. All I'm going to do is I'm just going to use it to maximize the self-consumption from my solar PV. Okay, so that's option one. Option two is a grid import only option. So basically, when the export tariff, is fixed, but the import tariff is time dependent, you basically charge the battery when it's cheap to charge the battery, but you only export when you've got excess solar PV. So you keep your battery topped up from the mains at a low rate, as and when it's beneficial for you to do so. And the third one is grid import and export. And this works best where you've got time varying tariffs for both import and export. And all this can be set up quite simply through the controls of the battery. Next, we're going to look at island mode. So if you want to use your battery as a backup power supply in the event of a power cut, that is not an automatic thing that every battery system will have. A lot of battery systems will not be able to give you backup power in the event of a power cut. You need to be able to electrically separate the battery from the incoming supply, and that's so you don't end up, in the event of a power cut, feeding electricity back into the grid from your battery, and potentially electrocuting people who are working on the supply side. So to do that, what you need to do is you need to set up what they call an island. And all an island is it's basically a big chunky relay that when it detects that the mains power is been switched off, it opens so that it electrically separates your power supply, your island, from the incoming supply and the main grid. With an island, you will still be able to charge your battery from PV during a power cut. If you don't have an island, you won't be able to do that. The PV will switch off and the battery will switch off. And the main reason, obviously, is to ensure safety of people who are working on the grid. upstream of you, and also so you're not ending up powering the neighbour's house from your battery. And basically, it can also be used depending where you put that relay. You can also separate backed up and non-backed up loads, and that can be quite useful if you have something like a heat pump or an electric vehicle charger, where you don't want those very high load devices to be powered from the battery, which would drain the battery pretty quickly. So typically, the things you'd back up would be probably a few lighting circuits, so you can move around the house safely. You'd probably put your fridge freezer on there. You'd probably put a few sockets on there so you can make yourself a cup of tea. You'd probably put your internet router on, so that you can at least watch, you stream things through to tablets, phones, etc. And you can keep an eye on what's going on, out and about, so you can still receive, you still maintain connectivity with the outside world, and you can know what's going on. So those are the things you typically back up. This island mode is not the same as a UPS, and we will and we'll talk about that a little bit in a moment. Because a UPS is what you use on an absolutely critical system. So if you're running a data center, if you're running a hospital, if you're running, if you've got a life support machine or some sort of oxygen system for a relative, or your partner or whoever at home, this backup battery capability is not what you need. There will be a small break in service as the contactor opens and the battery resumes operation. It'll probably be only a second or so. You're not talking about huge long periods without power, but it would be enough to, for example, maybe enough to drop a server or do something like that. So if you're running a data center, you need a UPS, which is a slightly different arrangement electrically. But what we're talking about here is sort of typical domestic situations. So the first thing to obviously bear in mind is we must make sure that we specified that we want backup capability. It's not an automatic thing. Because of this break, as the contactor opens, there will be a short break in supply, which means it's not suitable for sort of business critical systems or safety systems. And so that kind of sums it up, really. I'm not going to go into UPSs in this talk. It's quite a specialist area of design, but if that's something you're interested in, then obviously we can talk about it at another point. So this image here is actually from the Tesla app, but it gives you a pretty good idea of what you might see on your phone. So down here we have got the output from the Tesla Powerwall. Up at the top here, we are feeding 3.9 kilowatts in from the solar PV array, and our home is operating at 4.2 kilowatts. So you can see here that basically we're using solar, we're using a little bit of the battery, and that's all feeding into the house, and that changes in real time. So you can see here we're actually not on the grid at all at the moment. So what do the controls do? So they optimize the charge and discharge times to increase running cost savings. They can anticipate the solar. I think we've already talked a little bit about that. It's not quite as smart as perhaps it will be one day, but it doesn't take into account the vagaries of the weather forecast. But it does give you a pretty good insight into what it would typically expect to see from the solar PV. And it gives you real-time display of what your battery is doing, its state of charge. It also allows you to manage the backup power level, and that's simply literally a slider in the app, and you can change how much reserve you leave in the battery all the time for backup. And obviously, the more backup you leave in reserve, the longer that would last in the event of a power cut. But it also reduces the flexibility of the system on a day-to-day basis. So most people will leave that at a relatively low level to cope for that 10-15 minute power cut that happens every now and again. But say you get a weather warning and you know there's really high winds expected, and you know you're on an overhead line, you ramp that right up, and then you can you can make sure that you're covered for as long as possible. Okay. So hopefully let's have a quick can you show us some real battery storage pics? So it's just going through a few more questions. Do the battery controls learn from historic data usage to participate? Yes, they do. Obviously, each controller is slightly different. On a ground-mounted 10 kilowatt solar we have, if you have an existing inverter, do they usually allow for batteries to be retrospectively fitted? Yes, but you'd use an AC coupled system, so not the DC coupled one. But that's one of the reasons why AC is so popular, because people quite often put them on afterwards. And I think, Charles, I've already answered that question with the efficiency levels. Does the inverter and reversal process mean overall? It's that 3% rough loss compared to a DC coupled system. Please, can you share the formula to calculate the backup time of the battery? Yeah, it's a really simple one, that formula. But basically what you're looking at is the number of kilowatt hours that you have in the battery at the time that goes into backup, and then the load of that you're going to be taking out of that battery. So if you've got, say, a 2 kilowatt load on a 10 kilowatt hour battery, then that would last for 10 divided by 2, which is 5 hours, because the hours then cancel out. It all cancels out, so you get hours. But it's a fairly straightforward formula. Obviously, the more you add in terms of load, then the less time the battery lasts. The more backup you allow, the better. And can you show the real battery storage pics of any particular house which contains all the inverters and storages required? I don't think I've got any in this presentation, but there are. If you do it, I can easily send something out. But it will obviously depend on the actual installation and the type of battery. As I said, the Tesla systems are quite packaged, so you get relatively little external stuff, and quite often things will be in different rooms, etc. But there are, if you have a quick search on LinkedIn, there's loads of installers putting photos up of stuff they're installing. So have a little look around. Have a little look around LinkedIn, and you'll soon see these things. And then a question from Mohammed: are there any vehicle-to-home grid systems that are available at the moment? As far as I know, there aren't any that are commercially available. But I think there are some. I think Nissan, I think it is, are working on something quite actively, so that might be available soon. Okay, so red tape part. So we've already talked quite a lot about time of use electricity tariffs. So I'm not going to go too much into that again. But the main things to remember are obviously the wholesale cost varies every 30 minutes. So it's and the cost can actually be negative. And that's due to the fact that we're relying increasingly on wind and solar generation. Solar generation is still relatively small in the UK, but wind is quite a large part. And I think it was over the summer 47, 48%, something like that, of power was coming from renewables. So it's increasing all the time. And obviously this demand and supply thing. So a conventional electrical system can't store energy, so you've got to produce power and use it at the same time. And these time of use tariffs, the best known of those is the Octopus Energy Agile tariff, can exploit this to the benefit of battery owners. So let's have a look at the investment case. So this is where, obviously I've sort of talked an awful lot about the sort of upsides of batteries at the moment. There are some downsides. I mean, they are quite expensive to buy at the moment, and obviously they have a limited life. So when you take all that into account, and obviously, this is going to be very finger in the air, it's kind of rough figures. But at the moment, a kilowatt hour of electricity costs around about 10 pence to store. So if you're charging a battery with a kilowatt hour of electricity, it's going to cost you about 10 pence. At the moment, the difference between the peak import rate and the off-peak rate for electricity is also approximately 10 pence. So it doesn't take a genius to work out, but that means that batteries are pretty much cost neutral if you are just using mains to charge, discharge, etc. So where does it become beneficial? Well, the value is in the backup facility, and that can be very useful for some customers. And the other thing is where you've got solar PV. If you've got solar PV, you're producing that electricity for free. And if you can displace importing electricity, if you say you're exporting at 3 pence per kilowatt hour and it saves you importing at 15 pence per kilowatt hour or 18 pence per kilowatt hour, then that can be a real net benefit. So for most people, the investment case at the moment is quite shaky. I'm not going to sit here and say batteries are the answer to everybody's problems. They're not. But they're certainly worth considering, especially if you've got large PV arrays, especially if you've got a situation where you're in perhaps a really rural location and you're quite prone to power cuts. Those are the types of situations at the moment where it's a sensible investment from a purely economic point of view. Now let's think about this also. Time of use tariffs are becoming increasingly common. So these benefits are likely to increase. Greater grid flexibility is going to be required going forward because we are increasingly relying on wind and solar power. We're turning off, coal power stations haven't generated in the UK now for quite some time. We're this idea that you used to have this base load of the power stations would provide. Gas is becoming increasingly expensive to produce electricity from. The government are trying to push the green agenda, which is brilliant. It's all going to mean that the investment case of batteries is likely to become rosier and rosier as we go forward. Let's have a quick look at DNO permissions. So the distribution network operator, this is quite specific to the UK. But basically, if you're going to connect a generator to the network, then you may well require a permission from the DNO. A battery, although it only stores electricity, is counted as a generator. So G98, G99, and G100 regulations do apply. So you may be exempt from permission under G100 in certain situations. But basically what I'd say is if you're going to install a battery, talk to your DNO, talk to your distribution network operator about what you're planning to do. And they will tell you all the ins and outs and go through all the things with it. So a question from John Leach. Car batteries have a lifespan of about 2 years. What's the battery's life? So typically, a lot of the battery manufacturers are offering warranties of around sort of 5 to 10 year mark. But the actual life expectancy of the batteries is more than that. Most of them are sort of saying that they expect them to last about 20 years, which is similar to the life of a solar PV installation. A lot of that depends on the cell chemistry used, and obviously different cell chemistries have different costs. And I haven't really touched on the cell chemistry side, but yeah, you're not talking about 2 year lifespans. So don't worry about it from that point of view. They're talking about quite reasonable lifespans. Okay. Well, I've run over by about 10 minutes over what I wanted to. So we'll quickly run through the top 6 considerations for batteries. So first one, improve the building's fabric before applying renewable technologies. We say it every time. It's always number 1 on these considerations lists, but it still holds true with batteries. The next one is consider whether the backup of key services is required, and that will give you the answer as to whether just a battery on its own, no backup at all, is the best option for you. Whether a conventional backup system with the islanding relay is the best option, or whether you do need to go down the route of a full UPS system. If you've got key critical services, then a UPS is going to be required. Consider the likely usage patterns. How are we going to be using electricity? If you don't know, then actually, getting some data together before you install a battery might be a good idea. Because there's no point in installing a battery and then realizing that actually you never have any spare solar to put into it, or you're not really exporting anything, because then a battery is kind of a waste of time. So does a battery make sense for you? Then match the battery size to the demand, usage patterns, and on-site generation. The other thing is not just the battery size, but also the peak amounts of energy that the inverter can give you as well. Because there's no point in having a huge battery if you can't get that energy out of the battery fast enough. And use a time of use tariff to maximize savings. As I said, electricity cost varies up and down. A battery can really exploit that. That's where you can get the best out of it. And finally, before you do any installation, talk to your DNO, because it's just worth getting all those permissions in place, and avoiding any hassles of red tape further down the line. Okay. So I'm gonna quickly whiz through this slide, but this is where the space in which mesh work. So we're talking about here, this sort of first 2 steps, the feasibility and energy calculations. This is where we can sort of identify, is a battery likely to be a good option for you. Stage 4, we're talking about specification, and then finally, we can also use this feedback loop at stage 7. So you've got an existing building. Let's do some energy monitoring, and then see if retrofitting a battery might be a good idea, which then sort of takes us back around to sort of stage 4 kind of stage. So batteries definitely fit into this area, and obviously potentially fit into this area and this area too. So there's quite a lot of places where batteries could be a consideration. So any questions? Just go back one slide. Have they got any questions? Please type away into the chat window, and I'll do my best to answer them. So we've got a few questions up here. So Charles is asking how quickly we like to see like-for-like costs come down. That's a really good question. I would say that batteries are reducing in size, in cost. But if I had that crystal ball, Charles, then I wouldn't be sitting here giving you a presentation. I would be sat with my feet up on a desert island somewhere, having a lovely time. Patrick asks, can home generated wind energy be linked to battery storage? Yes, it can. It would be similar to PV, in that you'd have to obviously wind generates AC, so you'd need to you'd have effectively a sort of AC coupled system. You need some sort of power conditioning for it to feed to the battery in a nice way, but it can be done. So John's asking about battery sizes. So typically, I think I sort of talked about this a little bit earlier in the presentation, but for domestic installations, the sort of typical sizes are between about 5 kilowatt hours upwards. You can put multiple batteries onto a single system. So a little bit like when you get your AA batteries, and you'll see that quite a lot of things have multiple batteries in them. You can do that with with residential batteries as well. So, for example, the Give Energy system, they offer, I think it's 2.5, 5, and 8 kilowatt-hour batteries, and you can put up to, I think it's 5 of them in a single sort of array for one installation, and you can put them in any combination you like. So if you had 5 8 kilowatt-hour batteries, or then that's 5 8 of 40, that'd be 40 kilowatt-hours. Quite commonly with Tesla, for example, if you've got a 3-phase installation, then one of the options, and it's only one of the options, is to put a battery on each phase, which means that they're 13.5 kilowatt-hours each. So that's again sort of round about the 40 kilowatt-hour mark. So yeah, I mean, loads of choice from really quite small up to absolutely ginormous. And obviously, when you can start then looking at commercial size installations as well, where you can go up to, I think Australia are building some megalith battery at the moment out in the desert for this huge PV array they're putting in, which is going to be, I think it's sort of, they're talking about gigawatt hours of energy. Do you use the same batteries for multiple renewable technologies if you had both solar PV and wind? Yes. So Glyn, yes, you would be able to do that, because effectively what you're doing is if we go back, let me just see if I can find the slide, and where are we? So if we go back to AC coupled, and I'll have to just reshare this again. Just bear with me half a second. Share screen. That one. Share. So hopefully you can see that again now. But if you've got this AC coupled system, you could have multiple things feeding into the consumer unit from their own individual inverters or power conditioning things, and then have the battery inverter, and then have the battery. So you could have multiple technologies feeding in there. So that's certainly possible. So Mohammed's talking about car manufacturers reusing old electric car batteries into battery storage. Yes, that is a thing, and increasingly will be a thing going forward. Car batteries are quite the lithium-ion electric vehicle batteries are quite hard to recycle, but obviously the power density thing isn't such a massive issue with a home or certainly a commercial battery. At the moment, that's mainly being used actually for UPS systems on public buildings, where they already have big UPS rooms, which traditionally would have been lead acid batteries. So they're reusing lithium-ion batteries from cars. Already answered the one from Glyn. And Charles, most technologies do reduce in cost, particularly under mass adoption, as efficiencies of R&D deliver greater efficiencies. So get your deck chair ready on your desert island, David. Yeah, well, I mean, yes, obviously, these things, yes, we know, obviously costs do tend to come down. One of the sort of challenges at the moment in the battery industry is around the availability of certain chemicals and some of the constituents. So that without getting into the rights and wrongs of mining and all the other things that go along with this, it's certainly something that Tesla and other big battery manufacturers are trying to get to the bottom of, is how do they secure supplies of those key chemicals in a sort of justifiable, sort of environmentally and human rights justifiable way, because there are certainly issues around some of the supply chain at the moment. Okay, well, hopefully that's answered some of your questions on battery storage. Many thanks for all your time this morning. I'm just going to whiz through to the end of the PowerPoint again, because there is a thing about the various webinars we've got coming up. So we've got two more, one more before Christmas next week on Wednesday, and then we've got, and we've also got the first one for January already penciled in as well. So next week is I think it's a repeat of the Mesh Energy Zero to Hero, how to create sustainable architecture practice. So that's well worth a watch if you haven't seen it before. And then the what 2021 has in store for the sustainable design coming on the 6th of January. I won't be here again before Christmas, so have a great Christmas and New Year, everybody, and I will see you in 2021. Thanks very much.